In this lecture, I am going to present what is symmetrical frames and the analysis of symmetrical frames when the line of symmetry passes through column. Then I would like to solve one problem on symmetrical frame when the line of axis passes through column. What is symmetrical frames? If the frames and the loadings applied on them are symmetrical, first of all, there cannot be any side sways, and secondly, the bending moments in the frames would be symmetry. Therefore, it should be possible to make use of this advantage, analyze only the half of the structure, and by taking the advantage of symmetry to express the values for the other half. There are two cases of symmetry exist. The first one, the line of symmetry passing through the midspan of the beams, normally encountered when the number of bays are odd. Secondly, the line of symmetry passes through the column, which normally occurs when the number of bays is even. So here we will discuss the detail of the frames in which the axis of symmetry passes through the column. This case occurs when the number of bays is an even number. Due to symmetry of the loading and frame, the joints on the axis of symmetry will not rotate and hence are considered as fixed, and only one half may be analyzed. Because of symmetry, there cannot be any bending moments in the columns through which the line of symmetry passes. So look at this figure. So this is the original frame and this is two-story frame. Here there are two bays and two-story frame. And look at this figure. Here 4 bays and a two-story frame. In both the frames, the number of bays are even. So here there are 2 number of bays and here there are 4 number of bays. So when the number of bays are even, so the line of axis which passes through the column line. So here this is the line of axis which is passes through this column, and here in 4 bay frame line of axis which passes through this column. When the line of axis passes through the column, the original frame that you can substitute. So by taking the fixed end at the mid column of the frame. So here you have to apply the fixed end and here you have to apply the fixed end, and you have to analyze the substituted frame. Then the other half, so you have to put what is the value you got from this half, and the other half you have to put the same value but in opposite sign. The 4 bays and 2-story frame also you can substitute like this type of frame, and here, so this is the 2 bay where the axis passes through this column, that to join, that you have to treat it as a fixed end. Then you have to solve this substituted frame, and what is the value you get from this substituted frame? The other half you can put the same value but in opposite sign. Since the line of symmetry passes through column, only half of the frame considered for the analysis. This is the substituted frame, and here you can analyze this substituted frame, and what is the value you get from the analysis. For the next half you can put the same value but in opposite sign. Then coming to what are the step-by-step procedure to solve the symmetrical frames by Kanis method. As you know, the first step you have to determine the fixed end moments. Then you have to find out the relative stiffness of the members. Then you have to find out the relative stiffness of the joints. Then you have to find out the rotation factors. then determine the rotation moment by iterative process. So this is the formula. So by using this formula you can find out the rotation moments. M dash AB is equal to minus half KB by summation of KB into MFA plus summation of M dash BA. Summation of M dash BA, this is the sum of the far end rotation moments, and MFA, this is the fixed moment of the joint A, and this is minus half KB by summation of KB. So this is the rotation factor, and that you can denote by UAB. Then M dash AB is equal to UAB into MFA plus summation of M dash BA. So you can find out the near end rotation moment by using this formula. So you have to take the summation of the far end rotation moment plus the fixed moment of the joint, and you have to multiply with the rotation factor, and you have to find out what is the near end rotation moment. Then after getting the rotation moment, then you can find out the final moment. The rotation moment that you can find out in iterative process. The final moment that you can find out using this formula. So MAB and MBA, this is the final moment, and you can find out by the superposition of the three moments. The first moment, that is the fixed end moment of the end, then the twice the near end rotation moment plus once the far end rotation moment. So MAB is equal to MFAB plus twice M dash AB plus M dash BA. Similarly, MBA is equal to MFBA plus twice into M dash BA plus M dash AB. The moments M dash AB and M dash BA are called the rotation contribution, and this is called the rotation moment. The final moment is equal to fixed end moment plus twice the rotation contribution of near end plus once the rotation contribution of the far end. So by using this formula you can find out the final moment. So after getting the final moment, then you can give the direction of the moment, then you can draw the final bending moment diagram. Then coming to one example, analyze the frame shown in figure, taking advantage of symmetry of the frames and loading. So here this is 2 base and 2 story frame, and here A, B, C, D, E, F, G, H, I, and here the frame is given, the end A, F, G are fixed end, and the span of B and CD is given 6 meter, and span of EH and DI is given 6 meter, and the height of AB is given 3 meter, and the height of BC is given 3 meter, and the moment of inertia of CD and B is given 2I, and DI and EH is given 2I, and the moment of inertia of the column AB and BC is given I, EF and D is given I, and GH and HI is given I. So this is 2 base and 2 story symmetrical frames. The load on the top span is given 30 kilonewton by meter, and the load on the middle span is given, that is 20 kilonewton by meter. Since the line of symmetry passes through the column DEF, joint D and E will not rotate, only half of the frame considered for the analysis. So here D and E is not rotated, here the line of axis passes through the column DEF, so the D and E is not rotated, and here you have to consider half of the frame for the analysis. So what is the value you get from this half portion? Then for the other half you have to put the same value but in opposite sign. So here you have to consider D and E as a fixed end, and you have to take the substitute frame of this frame. So this is the substitute frame of the original frame, and here take D and E as a fixed end, and on the span B there is present 20 kilonewton by meter, and on the span CD there is present 30 kilonewton by meter load, and the moment of inertia of CD is 2I, and moment of inertia B is given 2I. As you know, the first step you have to find out what is the piston moments. So first you consider the span CD and find out what is the piston moment MFCD and MFDC. So MFCD is equal to minus WL square by 12. So here the W is given 30 kilonewton by meter and L is given 6 meter. So MFCD is equal to minus 30 into 6 square by 12 is equal to minus 90 kilonewton meter. And MFDC is equal to plus 30 into 6 square by 12, that is equal to plus 90 kilonewton meter. Then take span B and find out what is the piston moment MFB and MFE. On the span B, there is present the 20 kilonewton by meter load and the span is given 6 meter. So find out what is the piston moment MFB and MFE. MFB is equal to minus 20 into 6 square by 12 is equal to minus 60 kilonewton meter. And MFEB is equal to plus 20 into 6 square by 12, that is equal to plus 60 kilonewton meter. Then for the vertical member there is no load, so MFAB 0 and MFBA 0 and MFBC 0 and MFCB 0. Then the next step you have to find out the rotation factor. So here the rotation factor find out in a tabular form. Here you take 5 columns. The first column is joint, second column mention member, and third column relative stiffness of the member, and the fourth column that is the relative stiffness of the joint, and the fifth column show that is the rotation factor. So there are two joints. The first joint is your B and second joint is your C. So at the joint B, so there are three members meet, BA, BC and BE, and at joint C there are two members meet, CB and CD. So here you take two joints B and C. So at B, BA, BC, BE, three members meet, and at joint C there are two members meet, CB and CD. As you know, show how to find out the relative stiffness of the member. For vertical member AB, the relative stiffness is equal to I by 3, and for the vertical member BC, the relative stiffness is equal to I by 3, and for the horizontal member B, the relative stiffness is equal to 2I by 6, that is equal to I by 3. Similarly, the relative stiffness of the vertical member CB is equal to I by 3, and the relative stiffness of the horizontal member CD is equal to 2I by 6, that is equal to I by 3. So find out the relative stiffness of the members in a tabular form. I by 3, KBA I by 3, KBC I by 3, KBE I by 3, KCB I by 3 and KCD I by 3. Then find out the relative stiffness of the joint. So at the joint B, so there are three members meet, BA, BC, BC. So this is the relative stiffness of the member BA, KBA, this is KBC plus this is KBE. So here you find out the relative stiffness of the joint. K is equal to KBA plus KBC plus KBE. So as you know, KBA is equal to I by 3, KBC is equal to I by 3 and KBE is equal to I by 3. I by 3 plus I by 3 plus I by 3. So is equal to I. Then take the joint C. So at joint C there are two members meet, CB and CD. The relative stiffness of the member CB is equal to I by 3, that is KCB is equal to I by 3 and KCD is equal to I by 3. Then here find out the relative stiffness of the joint C. KC is equal to KCB plus KCD. So as you know, KCB is equal to I by 3 and KCD is equal to I by 3. So I by 3 plus 2I by 3 is equal to 2I by 3. Then after getting the relative stiffness of the joint, then find out the rotation factor. So by using this formula you can find out the rotation factor. So the rotation factor of the member, that is equal to minus half and the relative stiffness of the member divided by the relative stiffness of the joint. So here you know the relative stiffness of the member, this one, and this is the relative stiffness of the joint, and find out what is the rotation factor for the member BA. UBA is equal to minus half I by 3 divided by I. So this is equal to minus 1 by 6. Similarly, UBC is equal to minus half KBC divided by KB, I by 3 divided by I. So UBC is equal to minus of I by 3 divided by I. So this is equal to minus 1 by 6. Then find out UBE. So UBE is equal to KBE divided by KB. So KBE is equal to I by 3 and KB is equal to I. So UBE is equal to minus of I by 3 divided by I. So this is equal to minus 1 by 6. Similarly, find out the rotation factor for member CB and CD. UCB is equal to minus of KCB divided by the summation of KC. So this is the KC value and this is the KCB value. So here you find out the UCB is equal to minus of I by 3 divided by 2I by 3. So this is equal to minus 1 by 4. Similarly, find out the rotation factor UCD. So UCD is equal to minus of KCD divided by KC. So here KCD is given I by 3 and KC is equal to 2I by 3. So find out UCD is equal to minus of I by 3 divided by 2I by 3. So this is equal to minus 1 by 4. So these are the rotation factor for the member BA, BC, BE, CB and CD. Then find out the fixed end moments at joints. So as you know, at the joint B there are 3 members meet. So you know what is the fixed end moment of member B, MFB, but MFBC and MFBA 0. There is no loading on the vertical member. The fixed end moment at joint B is equal to 0 plus MFB. The sum of fixed end moment at B is equal to MFB is equal to MFBA plus MFBC plus MFB. MFBA and MFBC both are 0 and MFB the value you got here minus 60 kilonewton meter. So 0 minus 60, this is equal to minus 60 kilonewton meter. Then find out the sum of fixed end moment at joint C. At joint C there are 2 members meet, CB and CD. So you know what is the fixed end moment MFCD, but on the vertical member CB there is no loading. So MFCB is equal to 0. So the fixed end moment at joint C is equal to 0 minus this one 90. So MFCD is equal to minus 90, 0 minus 90. So the sum of fixed end moment at C is equal to MFC is equal to MFCB plus MFCD. So 0 minus 90 is equal to minus 90 kilonewton meter. So this is the fixed end moments. So then find out the rotation moments. In this tabular form, find out the rotation moments. So here there are 2 joints, one joint B and second joint is your C. And this is the substituted frame A, B, C, D, E. So at a joint B, so make 2 rectangle and at joint C make 2 rectangle, one large rectangle then one small rectangle. Here also make one large rectangle and inside make one small rectangle. At B, so this is the larger rectangle, this is smaller rectangle, and at C this is larger rectangle, this is smaller rectangle. What is the fixed end moment of joint B? You got, just you write in the inner rectangle, small rectangle. And what is the fixed end moment of joint C? You got, write in the inner rectangle or smaller rectangle. Here the fixed end moment of joint B is equal to minus 60 and fixed end moment of joint C is equal to minus 90. Then here you got the rotation factor for the member BA, BC, BE. For BA minus 1 by 6, BC minus 1 by 6 and BE minus 1 by 6. So this is BA, this is BE and this is BC. The rotation factor UBA put in this rectangle and the rotation factor UBE put in this rectangle and the rotation factor UBC put in this rectangle. So this is UBE, this is UBA and this is UBE and this is UBC. Then what is the piston moment? You got MFBE, so that you put here, and MFEB you put here. Just above the line, write the piston moment of the end of the members. So MFBE, that you got minus 60, just to write above this line, and MFEB you got plus 60 kilonewton meter, so write above this line. Similarly, the MFCD and MFDC, just to write above this line. So MFCD you got minus 90 right above this line, and MFDC you got plus 90 right above this line. After putting the piston moments of the end of the members, piston moment of the joints, and the rotation factors, this is the rotation factor, this is the rotation factor UCB, right in this trapezium box, and UCD right in this trapezium box, minus 1 by 4. This is UCB minus 1 by 4 and UCD minus 1 by 4. So this rotation factor UCB and UCD write the corresponding trapezoidal box, minus 1 by 4, minus 1 by 4. Then these are the rotation moments. The rotation moments that you find out by iterative technique. Find out the rotation moment. The rotation moment can be determined by iteration process. So first you go for the cycle 1 and you go to joint C. When you are considering joint C, here you know what is the piston moment, MFCD minus 90, vertical member of piston moment is your 0. And you have to find out what is the near end rotation moment, M-CD and M-CB. So the near end rotation moment that you can find out by taking the rotation factor into the piston moment of the joint plus the summation of the far end rotation moment. In first cycle, at the end D is fixed. Here you take the far end rotation moment 0, and M-BC assume the far end rotation moment is your 0 in first cycle, and find out what is the near end rotation moment, M-CD and M-CB. First you go to the joint C, MFC, sum of piston moments at C is equal to minus 90 kilonewton meter. Then summation of M-BC, this is the rotation moment of far ends of member meeting at joint C. We know M-DC is equal to 0 due to fixed end D, In first cycle, M-BC is assumed 0. Then by using this formula, so find out what is the near end rotation moment, M-CB and M-CD. So M-CB is equal to UCB into MFC plus summation of M-BC. You know UCB is equal to minus 1 by 4 into the piston moment of joint C minus 90, and this side the far end rotation moment 0, and this side also the far end rotation moment 0 in first cycle. So minus 1 by 4 minus 90 plus 0, this is equal to plus 22.5 kilonewton meter. Then find out the near end rotation moment M-CD. So M-CD is equal to UCD into MFC plus summation of M-DC, sum of the far end rotation moment. So here the sum of the far end rotation moment in first cycle, this is 0, and this side also 0, and this is the piston moment, and this is the rotation factor. So M-CD is equal to minus 1 by 4 into minus 90 plus 0 and plus 0. So this is equal to plus 22.5 kilonewton meter. At joint C, you got the two near end rotation moment. Then you put the near end rotation moment M-CB 22.5 kilonewton meter and M-CD 22.5 kilonewton meter. So just below the line, so write the near end rotation moment 22.50, and here also you write the near end rotation moment 22.50. Then you go to the joint B. So at joint B there are three members meet, BA, BC and B. When you are considering the joint B, so here you have to take the far end rotation moment M-AB, M-CB and M-CB. This is the fixed end moment of the joint B, and these are the rotation factors. You got at joint C, so what is the near end rotation moment M-CB? So this M-CB, when we are considering the joint B, so this moment you have to take as a far end rotation moment, so you have to take 22.50 that is m dash cb. As the end is fixed, so here you have to take the rotational moment is 0 due to the fixed end at A. So here also you have to take the rotational moment is 0. So this side you have to take 0, this side you have to take 0, and here you got the 22.50 the rotation moment. So find out the near end rotational moment m dash BA, m dash BE and m dash BC and put here. MFB, the sum of fixed end moment at B minus 60 kilonewton meter, summation of m dash AB, rotational moment of far end of members meeting at joint B. We know m dash AB is equal to 0 due to fixed end A, m dash EB is equal to 0 due to fixed end E, and m dash CB is equal to 22.50 kilonewton meter. Then you can find out the near end rotational moment m dash BA is equal to UBA into MFB plus summation of m dash AB. M dash BA is equal to minus 1 by 6 minus 60 plus 22.5 plus 0 plus 0. So this is equal to 6.25 kilonewton meter. Similarly, m dash BC is equal to UBC into MFB plus summation of m dash BC, the sum of the far end rotation moment. So here m dash BC is equal to minus 1 by 6. So this is the fixed end moment and this is the far end rotation moment. So you got the far end rotation moment m dash CB is equal to 22.50, and at other fixed end the rotation moment take 0. So 22.5 plus 0 plus 0, this is equal to plus 6.25 kilonewton meter. Then find out m dash B. M dash B is equal to UB into MFB plus summation of m dash B. So UB is equal to minus 1 by 6, MFB is equal to minus 60, and summation of m dash B 22.5 plus 0 plus 0. This is equal to 6.25 kilonewton meter. Then you put the value of rotational moment m dash BA here and m dash BC here just below the horizontal line, and m dash BC put here 6.25. Then the first cycle is over. Then you go for the second cycle. Again you find out what is the near end rotation moment at joint C and at joint B. Go for the second cycle. Then again you go to the joint C, and you know the sum of the fixed end moment at joint C minus 90 kilonewton meter, and the rotation moment of far end of member meeting at joint C, summation of m dash BC. You know m dash DC is equal to 0 due to fixed end, and m dash BC is equal to 6.25 kilonewton meter. So when you are considering joint C, at joint C two members meet, CB and CD. So here already you know, so 6.25 kilonewton meter, 6.25 kilonewton meter at the joint B. When we are considering joint B, so here you got the near end rotational moment 6.25, 6.25, 6.25. In second cycle, when you are considering the joint C, so this 6.25 you have to take as the far end rotational moment m dash BC, and this side as the end is fixed, so you have to take the far end rotational moment is equal to 0. Then find out what is the value near end rotational moment at joint C, m dash CB and m dash DC. So in second cycle, so this is the value 20.94, 20.94. So here you find out the m dash CB and m dash CD. So m dash CB is equal to UCB into the fixed end moment of joint C plus the summation of far end rotation moment at the joint C. So the UCB is, you know, minus 1 by 4, and the fixed end moment of joint C minus 90, and the far end rotation moment, you know, one side 6.25, and at the fixed end the far end rotation moment is equal to 0. So m dash CB is equal to 20.94. Similarly find out m dash CD. So UCD into MFC plus summation of m dash DC. So UCD is, you know, minus 1 by 4, MFC minus 90, and summation of m dash DC, this is 6.25 plus 0. So this is equal to plus 20.94 kilonewton meter. So here you got the near end rotational moment m dash CB and m dash CD 20.94 kilonewton meter. So here you put 20.94 kilonewton meter and 20.94 kilonewton meter. Just below the first cycle rotation moment. Then you go to the joint B. So at joint B, 3 members meet, BA, BE and BC. When you will find out the near end rotational moment at joint B in second cycle, you have to take the far end rotational moment. At the joint A this is 0, at joint E this is 0 due to friction, and here you have to take the far end rotational moment m dash CB 20.94. This side you take 20.94, this side 0 and this side 0, and find out what is the m dash BC and m dash BE and m dash BA. So m dash BC is equal to UBC into MFB plus the summation of m dash CB. So the summation of m dash CB, so the far end rotational moment. So this side you take 20.94, this side you take 0, this side you take 0, minus 1 by 6 into minus 60 plus 20.94 plus 0 plus 0. plus 0 plus 0. M dash B is equal to minus 1 by 6 minus 60 plus 20.94 plus 0 plus 0. So this is equal to plus 6.51 kilonewton meter. Similarly, m dash BC is equal to UBC into MFB plus summation of m dash BC minus 1 by 6 minus 60 plus 20.94 plus 0 plus 6.51 kilonewton meter. Similarly, m dash B is equal to minus 1 by 6 minus 60 plus 20.94 plus 0 plus 0. This is equal to plus 6.51 kilonewton meter. Then you put the value just below the first cycle reading. So in first cycle you got 6.25, 6.25, 6.25, and in second cycle you got 6.51. Just you put just below the first cycle rotation moment value. So 6.25. So second cycle you got 6.51, 6.51, and 6.51. So in the similar way, then you go for the third cycle. And first you go to the joint C. So at joint C, you have to take the far end rotational moment m dash BC, this side 6.51 and this side 0, and find out what is the near end rotational moment m dash CB and m dash CD. So m dash CB is equal to UCB into MFC plus the summation of m dash BC. M dash CB is equal to minus 1 by 4 into minus 90 plus 6.51. What is the value you got in the second cycle? So that rotational moment you have to take here. So 6.51 and this side 0. M dash CB is equal to minus 1 by 4 into minus 90 plus 6.51 plus 0. So this is equal to minus 1 by 4 minus 90 plus 6.1 plus 0. This is equal to plus 20.87 kilonewton meter. Similarly, find out m dash CD, UCD into MFC plus summation of m dash DC. So minus 1 by 4 into minus 90 plus 6.51 plus 0 plus 20.87 kilonewton meter. Then you put the value. This is 20.87. This is 20.87. The third cycle reading you put below the second cycle reading 20.87 and 20.87. Then you go to the joint B. Similarly, you find out what is the third cycle reading 6.52, 6.52, 6.52. Then you go for the fourth cycle. So in fourth cycle, go to the joint B and find out what is the near end rotation moment. Here you got the near end rotation moment 20.87 and m dash CB you got 20.87 and m dash CD you got here 20.87. So, but here you see the third cycle reading and the fourth cycle reading, there is no difference. Then you go to the joint B. So at joint B, similarly find out the fourth cycle readings m dash BA, m dash BE and m dash BC. So m dash BA this is 6.52, M dash B 6.52 and M dash BC 6.52. So here you see there is no difference between the third cycle and fourth cycle. Then you stop here, then find out the final moments. So this is the third cycle 20.87 at joint C 20.87 and at joint B. So this is M dash BA 6.52, M dash BC 6.52 and M dash B 6.52. Then again go for the fourth cycle. So at fourth cycle M dash CB is equal to 20.87 and M dash CD is equal to 20.87. So there is no difference between the third and fourth cycle reading 20.87. Similarly at joint B, so M dash BA is equal to 6.52, M dash BC 6.52 and M dash BE 6.52. So there is no difference between the third and fourth cycle reading. 6.52 this is third cycle reading and this is third cycle value. M dash BA, M dash BC, M dash BE 6.52 kilonewton meter and this is the fourth cycle value 6.52 kilonewton meter, 6.52 kilonewton meter and 6.52 kilonewton meter. So in tabular form, this is the third cycle rotation moment M dash BA, this is fourth cycle rotation moment M dash BA and this is the third cycle rotation moment M dash B, this is fourth cycle rotation moment M dash B and this is third cycle rotation moment M dash BC, fourth cycle rotation moment M dash BC. Similarly M dash CB third and fourth 20.87 and M dash CD third and fourth 20.87. Here you stop the iterative process and find the final moments. This is the rotation moment M dash AB 0, M dash BS plus 6.52 kilonewton meter, M dash BC plus 6.52 kilonewton meter, M dash BE plus 6.52 kilonewton meter, M dash EB 0, M dash CB plus 20.87 kilonewton meter, M dash CD plus 20.87 kilonewton meter and M dash DC 0. And these are the fixed end moments. Already you got MFCD minus 90 kilonewton meter, MFDC plus 90 kilonewton meter, MFB minus 60 kilonewton meter, MFEB plus 60 kilonewton meter. Then find out the final moments. So by using this formula you can find out the final moment. MAB is equal to MFAB plus twice the near end rotation moment plus 1 the far end rotation moment. So MFAB 0, M dash AB 0 and M dash BA 6.52. So MAB is equal to 6.52 kilonewton meter. Similarly MBA is equal to MFBA plus twice M dash BA plus M dash AB. 0 plus 2 into 6.52 plus 0, this is equal to 13.04 kilonewton meter. Then MBC is equal to MFBC plus twice M dash BC plus M dash CB. So this is equal to the fixed moment of BC 0 and twice the rotational moment M dash BC 2 into 6.52 and once the rotational moment M dash CB plus 20.87. This is equal to 33.91 kilonewton meter. Similarly the moment MB is equal to MFB plus twice the near end rotational moment B and 1 the far end rotational moment EB. Minus 60 the fixed end moment MFB minus 60 plus 2 into 6.52 2 into 6.52 plus 0, this is equal to minus 46.96 kilonewton meter. Then MCB is equal to MFCB plus twice M dash CB plus M dash BC. 0 plus 2 into 20.87 plus 6.52 is equal to plus 48.26 kilonewton meter plus 48.26 kilonewton meter. Then MCD is equal to MFCD plus twice M dash CD plus M dash DC is equal to minus 90 plus 2 into 20.87 plus 0 is equal to minus 48.26 kilonewton meter. Then MDC is equal to MFDC plus twice M dash DC plus M dash CD plus 90 plus 0 plus 20.87 is equal to 110.87 kilonewton meter. Then MEB is equal to MFEB plus twice M dash EB plus M dash B is equal to plus 60 plus 0 plus 6.52 is equal to 66.52 kilonewton meter. So these are the final end moments of the substitute frame. After getting the value for the substitute frame, then the other half you have to put the same value in opposite side. So this is the value you got, the final end moment MAB, MBA, MBC. So here this is the full frame, so this is the half frame and this is the another half frame. So here you got MAB is equal to 6.52 kilonewton meter, this is MAB, and here this side in opposite side MGH, so here you put minus 6.52 kilonewton meter, and here you got MBA is equal to 13.04 kilonewton meter, here you got MBA is equal to 13.04 kilonewton meter, and here you put MHG is equal to minus 13.04 kilonewton meter. Then here you got MBC is equal to 33.91 kilonewton meter, and here you put MHI is equal to minus 33.91 kilonewton meter, and here you got MCB is equal to 48.26 kilonewton meter, here you put, and opposite sign here you put MIH is equal to minus 48.26 kilonewton meter. Then MB you got minus 46.96 kilonewton meter, and here you put MHE plus 46.96 kilonewton meter, and here you got MEB 66.52 kilonewton meter, and here you put MEH minus 66.52 kilonewton meter, and here you got MCD is equal to minus 48.26 kilonewton meter, and MID put 48.26 kilonewton meter, and MDC 110.87 kilonewton meter you got, and MDI here you put minus 110.87 kilonewton meter. So this is the moment of the full frame. So here you analyze half portion of the frame, and for the full frame, so here you put the value in opposite side. Then after knowing the moments, then you keep the direction of the moments. As you know, the positive moment the direction is clockwise, and for negative moment the direction is anti-clockwise. So as per sign convention, here you put the direction of the moment. You know MAB plus 6.52, so give the direction clockwise, and you know MBA also plus 13.04 give clockwise, and MBC plus 33.91 give the direction clockwise. But you know MBE, the value you got here minus 46.96, so here you give the direction anti-clockwise. So this is clockwise, and this is anti-clockwise. Then you check at joint B whether the sum of the moment is coming 0 or not. So here this is 13.04, this is 33.91, both equal to, this is 46.96 kilonewton meter. So similarly here M dash CB 48.26 clockwise, and M dash CD minus 48.26, this is anti-clockwise, 48.26 minus 48.26. Similarly at joint E, so here this is clockwise and this is anti-clockwise, positive moment, this is negative, positive clockwise, this is negative anti-clockwise, and here also this is clockwise, this is anti-clockwise, positive and negative, this is positive, negative, clockwise, anti-clockwise, and here also this is anti-clockwise, this is clockwise, and this is anti-clockwise. 13.04, 33.91, this is 46.96. Anti-clockwise, this two is anti-clockwise and this is clockwise. Negative, negative, anti-clockwise, and this one is clockwise. And here also this is anti-clockwise and this is clockwise. These are the direction of movements. Then after knowing the direction of movement, then you can draw the final bending moment diagram. Here you see the arrow mark is towards inside, and here the arrow mark is towards outside. Draw one line 6.52, and here you draw 13.04. Then you join these two points. This is 13.04 and this is 6.52. Then join these 2 points. If the tension is inside, then you take positive. If the tension is outside, then you take negative. 13.04 and this side 6.52. Similarly here for the member CB, so this is inside and this is outside. So inside 33.91 and this is outside 48.26. So here you take a 33.91 and here you take 48.26, then join these 2 points, and this is the BMD of the vertical member BC. 48.26 and this 33.91, so this is negative and this total is positive. Similarly draw here for the horizontal member B, so here given 46.96 and this side is given 66.52. So here you draw 46.96, 66.52 and this side also 46.96, 46.96. Then join these points and this is the negative bending moment diagram for the horizontal member. Similarly here also for horizontal this is 48.26 and this is 110.87, this is 48.26. So here you take 48.26, 110.87, 48.26 and join these points, and this is the negative bending moment diagram of the top horizontal member. And for this member, so here this side 48.26, this side 33.91, so draw this side 48.26, draw this side 33.91 and join these 2 points. Now this is negative and this is positive. Similarly here also take 13.04 and take this side 6.52, then join these 2 points. This is negative and this is positive. This is the negative bending moment diagram. The red line which marks here, this is the negative bending moment diagram, except tension inside, that is positive. Then as you know, so what is the load is given on the beam, so from that loading, so you can draw the free bending moment diagram. Here given the UDL 30 kilonewton by meter and here given the UDL 20 kilonewton by meter. Here you draw the free bending moment diagram, so that will be parabolic, the free bending moment diagram. So for this one W L square by 8, 30 into 6 square by 8, and for this one also 30 into 6 square by 8. Similarly for the span B, so here the load is given 20 kilonewton by meter, the free bending moment diagram, this is 20 into 6 square by 8, and for this span EH, here also 20 into 6 square by 8, and the bending moment diagram is, the free bending moment diagram is parabolic. So here you take this is parabolic, and here also you take this is parabolic, this is also parabolic, and this is parabolic. And find out this value. This is 30 into 6 square by 8, and here this is also 30 into 6 square by 8, and this value is 20 into 6 square by 8, and this value is 20 into 6 square by 8. So this is the positive bending moment diagram. Then the net, the positive and negative, the overlapping portion is cancel each other here, and this is also cancel each other, this is cancel each other. So this is negative, positive, negative, positive, negative, and here this is negative, this is positive, and this portion is cancelled, and here this portion is negative, this portion is negative, and this is positive. Similarly this is negative, positive, and here this is negative, this is positive, 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 negative, this is positive, negative, positive. So this is the final bending moment diagram of the 2-story and 2 base frame when the axis of symmetry passes through the column. Now all are clear. So how to analyze the symmetrical frame when the axis of symmetry passes through the column line.